It says let E be a subset of the real numbers. If E is non-empty and has some upper bound, we define should E to be the least upper bound of E. This is well defined by theorem 1.9. We introduce the two additional symbols plus infinity and minus infinity. If E is non-empty and has no upper bound, we said sub P is plus infinity. Sub P plus infinity we put when if E is non-empty and not bounded above. Again, if E is empty, we said sub P equals minus infinity. Now you may be having a question. අපි ඒකට හේතුව තේරෙනවද? I'm talking singular by the way. If E is empty, we said sub E to be minus infinity. Do you understand why?
Yeah, then the upper bound can be from minus infinity to plus infinity.
That's the reason. The least one must be minus infinity. We refer to sub E as the supremum of E. The funny thing is, by the way, I shouldn't say it now. Next week. We refer to sub E as the supremum of E and also denote it by sub E. So sub E, I was introduced this thing when I was in Colombo University. So I was asking my friends, do we have vegetable soup? Not really soup. Yeah, these are kind of, So, if E is non-empty and bounded above, he has proved that. I have to present the proof to you, this proof. He has proved that it has a least upper bound. And we have proved earlier, went through the proof that if a set is bounded above, it has at most one least upper bound. If the set is not bounded above, we say the sup of that set is infinity. The word infinity is just a symbol, by the way, here. We haven't discussed about anything. And if it is empty, as you told me, the set is sub E is minus infinity. And you gave me the reply. Thank you for that. Many people cannot give that answer. Reason. At present, plus infinity and minus infinity are meaningless symbols. He said that. That's very good because we don't know anything. We have no operations on them at present, and none of our results involving real numbers apply to plus infinity and minus infinity because these are not real numbers. In section 6.2, we add plus infinity and minus infinity to the reals to form the extended real number system. That is called extended real number system. We have the real number system, then R union set containing minus infinity and plus infinity is called the extended real number system. Real numbers. Okay, extended real numbers. But this system is not as convenient to work with as the real number system because many of the laws of algebra break down. For instance, it is not a good idea to try to define plus infinity plus minus infinity. It is meaningless. And setting this equal to 0 causes not some problems, so many problems. Infinity minus infinity has no meaning. There is a good one, I hope we have time, yes. It says you know that there is no rational number R such that R squared is equal to 2. We have proved it. But here he says there exists a positive real number x such that x squared is equal to 2. Understand? There is no rational number x such that x squared equals to, but definitely there is a positive real number x such that x squared is equal to 2. So this is an important theorem. So as a result, we should go through it. Comparing this result with proposition 4.4.4, we see that certain numbers are not real but rational. So the proof of this proposition also shows that the rationals Q do not obey the least upper bound property. Otherwise, one could use the that property to construct a square root of 2, which by proposition 4.4.4 is not possible. We have proved that there is no rational number x such that x squared equals 2. Okay, this proof is also important for you. When I say important, because we try to write square root of 2 is 1.414 blah 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 without quitting anywhere. So it seems that there is a real number x such that x squared equals to 2. There is, but we cannot write. We cannot write. Okay, let's go through the proof very carefully. Let E be the set of all y belongs to R such that y greater than or equal to 0, y squared is strictly less than 2. We take this set. If you don't understand any little tiny detail, you have to ask me. Thus, E is the set of all non-negative real numbers whose square is less than 2. Right? Observe that E has an upper bound of 2. Can you see that E is an upper bound? Sorry, 2 is an upper bound. Because if y greater than 2, then y squared greater than 4, greater than 2, and hence y does not belong to 2. Numbers greater than 2 are not in this set. Also is non-empty, for instance, 1 is an element of it. 1 belongs to it. Thus, by the least upper bound property, E is a subset of R, non-empty, bounded above by 2 at least. At one property we have a real number x, we denote by sub E. Right? Now we know this set has a supremum. It is, we are going to say it is sub E. He is saying it is x, which is the least upper bound of E. This set has a, because it is bounded above, it has a least upper bound from the previous theorem. Then x is greater than or equal to 1. X is the supremum of the set. 1 is an element, therefore x must be greater than or equal to 1. And less than or equal to 2, why? 2 is an upper bound and x is least upper bound. Right? So x is positive, x lies between 1 and 2, x must be greater than 1, so greater than 0, therefore x is positive. Now we show that x squared equals 2. So can you see this is another thing you learn from here. When you use there exists in maths, there exists now. It's like in religions, you said you are Catholic, they believe in heaven. If I ask them where is it, can I take the highway bus? No. So it is, Christians say, I was in US, people they call it Nirvana. I don't know whether you have heard. So, I don't know anybody who has been to Nirvana. However, Buddhism says that in Christians they believe in God. If you take an American coin, $1 coin or $1 coin, it is written there. We believe in God. It is a belief. But in Buddhism, they say we don't have to believe in Buddha. We can criticize anything. We can agree, disagree. That's why it is Western world, they say Buddhism is not a religion, it's a philosophy of life. So it has some truth. So in any religion, they believe in something. Otherwise you cannot make a living, no? You are a Buddhist. So I am sure you believe that there was a person called Buddha, no? He had a beautiful wife called Yasodhara, etc. In life we have to believe certain things. We cannot get rid of that. So, same way these rational numbers, when they say they are like this, it must be there, but who knows what they are. Now we are going to prove that x squared is equal to 2. Now it's very important. We spent time to show that there is no rational number whose square is 2. We have proved that. Now we are saying we can write it and show it, but we are saying there is something. It is there. Can you write? Somebody asked me. I say no, I cannot write. If I can write a number, most probably it is a rational number. Now since you came to this class, now you know how to write some irrational numbers. No? That day I told you, no. So again, you don't know yet, that is an irrational number. Next section you have to prove it. I will come back to that even if it is not in the book, because I want to bring good analysis problems to the class. Now we want to show that this number x, which is the supremum of this set, satisfies the condition x squared is equal to 2. We cannot write. Now if you take the interval set of all real numbers between 0 and 1, including 0 and 1, it has a sup which is equal to 1. Actually you can prove it, but I did not spend time in proving it. But you take it for granted from the bottom of your heart, the sup of that set is 1. There is no question about it to you. Here it is not like that. X is somewhere on earth, who knows. But we are going to prove that x squared is equal to 2. We are going to use the fact that this trichotomy. If we know there is no, that's what the previous theorem said. So there is something called sup, least upper bound. We know that it is there, we don't know what it is. Because it is a real number, it should satisfy this trichotomy. X squared less than 2, greater than 2, and equals to. So we are going to prove that both x squared 2 and x squared greater than 2 is not going to happen. What remains is then x squared is equal to 2, and that is the proof. Let's see how it works. He says we argue by contradiction. Let's see. We show that both x squared less than 2 and x squared greater than 2 lead to a contradiction. So, let's see. First, suppose that x squared less than 2. And we take a number, epsilon, positive number between 0 and 1, excluding 0 and 1. Of course, 0 is excluded because 0 is non-negative but not positive. Be a small number. Then we have x plus epsilon squared is x squared plus 2 epsilon x plus epsilon squared. Since x less than or equal to 2, this x can be replaced by 2. No? X less than or equal to 2, then 2 epsilon x less than or equal to 4 epsilon, right? And then you get, here you had epsilon squared, because epsilon is strictly less than 1 and positive, epsilon squared less than epsilon. So that's how he got the third epsilon, right? Then x squared plus 5 epsilon. So we are saying x plus epsilon squared is strictly less than x squared plus 5 epsilon, right? Since x less than or equal to 2 and epsilon squared less than or equal to epsilon. Since x squared less than 2, we see that we can choose an epsilon between 0 and 1 such that x squared plus 5 epsilon also less than 2, because there is a gap, no? 2 is here, x squared is here. So there are numbers. I choose a small guy, epsilon, x squared plus 5 epsilon also is strictly less than 2. That we can do. Thus, x plus epsilon whole thing squared, if now we have here x plus epsilon squared less than or equal to x squared plus 5 epsilon. If x squared plus 5 epsilon is right here, then it is strictly less than 2, right? By construction of A, this means that x plus epsilon belongs to E, because E is the set of all real numbers, non-negative, whose square is strictly less than 2. Now we have x plus epsilon whole thing square less than 2. Therefore, x plus epsilon must belong to the set. X is an upper bound, actually least upper bound, and x plus epsilon is a member. X plus epsilon greater than the least upper bound, which is a contradiction. But this contradicts the fact that x is an upper bound of t. Right, no? So now we have shown x square 2, x square less than 2 cannot hold. We have shown. Now we have to show that x square greater than 2 cannot hold either. Again we take a number epsilon between 0 and 1. I told you, no, when you begin analysis, till you die, epsilon. Let 0 less than epsilon less than 1 be a small number. Then, can you see, I mean, by writing small, it's redundant, no? No use, no? Actually, they are not small.
Yeah, it's subjective.
Yeah. I mean, that's sort of in real maths, no, in the logical thing. Then we have x minus epsilon whole thing square is x square minus 2 epsilon x plus epsilon square greater than or equal to x square minus 2 epsilon x, right? Because epsilon I removed it. Again here he has said minus 2 epsilon x greater than minus 4 epsilon because x is less than 2, right? Since x less than or equal to 2 and epsilon square greater than or equal to 0. Since x square greater than 2, we can choose now 0 epsilon less than 1 such that x square minus 4 epsilon also greater than 2. X square, if it is greater than 2, you can choose a small number between x squared and 2. So that is, he has written x minus 4 epsilon. And thus, x minus epsilon whole thing squared greater than 2. So that is that. Oh, can you see? Now, over there, he wrote let 0 less than epsilon less than 1. This epsilon is not that one. Here's what he is saying. X minus epsilon, you can make it small enough so that it is x minus epsilon square greater than 2. But this implies that x minus epsilon greater than or equal to y, all y belongs to E. Why? Because in the set E, all numbers x squared is less than 2. Now here x minus epsilon squared greater than 2. Therefore x minus epsilon greater than or equal to y, for all y belongs to E. He says y, if x minus epsilon is strictly less than y, then x minus epsilon square is strictly less than y square. So this epsilon, x minus epsilon must be greater than 0 to say so. And then less than y square, less than or equal to 2, this is a contradiction. Then from over there you get x minus epsilon is an upper bound of E. At the same time, x minus epsilon square less than or equal to 2. Which contradicts the fact that x is the least upper bound of E. From these two contradictions, we see that x square is equal to 2 as desired. So what we have shown is that actually we did not prove x square is equal to 2. We proved that
Other possibilities can't happen.
other possibilities cannot happen. So it is a good proof, and it's the standard proof. Other people write the same thing in different ways, but it is a good proof. Remember now that square root of 2 is because of this axiom. Actually because of this least upper bound property. That's why, otherwise nothing, no number x such that x squared is equal to 2. Here actually, sup of the set, sup is something who knows where it is. But we have shown that it x squared cannot be less than 2 and it cannot be greater than 2. So what remains must be true. So it's not tangible. Remark 5.5.14. In chapter 6 we will use the list upper bound property to develop theory of limits, which allows us to do many more things than just take square roots. Something came to my mind. You told me you will give me some, because this Friday,
Yeah, I'll give you the questions.
today you are giving me. Okay, I want to take a look. In chapter 6 we will use the list upper bound property to develop the theory of limits, which allows us to do many more things than just take square roots, whole bunch of things. We can of course talk about lower bounds and greatest lower bounds of sets. The greatest lower bound of a set E is known as the infimum, that's the word. Over there, supremum. Here, when it comes to the greatest lower bound, we call it infimum of E and is denoted by inf E. Everything we say about suprema has a counterpart for infima. We will usually leave such statements to the reader. The precise relationship between the two notions is given in exercise 5.5.1. Let's read that anyway. What does it say? Let capital E be a subset of real numbers, and suppose that E has a list upper bound M, which is a real number, that is capital M equals to E. Let minus E be the set. Minus E is set of all minus x, such that x belongs to E. Show that minus M is the greatest lower bound of minus E. So minus M is equal to infimum of minus E. That's right. So I'm not going to do that exercise because you must do it. Over here we have that question, our thing that we didn't do. Both 5.2, 5.3 are related to that theorem that he said most of the things will be left out as exercises. So he's, giving us hard parts like this. Real exponentiation, part 1. So, very important now that you know, to a man in the street, he cannot understand that there is a number x such that x squared is equal to 2, because he is thinking of actually numbers, those can be written. They are rational numbers always. So, but he himself knows that this Pythagorean theorem, if you take each side is 1 unit, right angle triangle, then the hypotenuse satisfies the condition x squared is equal to 2. But in the real line, for the hypothesis, we cannot measure. No? If I say I am 5.5 feet and 11 inches tall, no, anybody can challenge that it is not true. Because how can you measure height? So these are not, you cannot measure exactly. Nobody can come up with tools that can measure things exactly correct way. My height can be 5.11, 0.1, 0.01, 0.001. Then how can you measure? Yeah, anyway, let's see. In section 4.3, we define exponentiation, x to the n when x is rational, and n is a natural number, or when x is non-zero rational, and n is an integer. We did that. Now that we have all the arithmetic operations on the reals, we can similarly define exponentiation for the reals. That's what he says. We are constructing real numbers. Still. Let's see, he says exponentiation by a real number by a natural number, let x be a real number. To raise x to the power 0, we define x to the 0 equals 1. Now, suppose recursively that x to the n has been defined. Some other thing I am uncomfortable with the English here. Now suppose recursively that x to the n has been defined. How can you suppose recursively? No, he he is using the fact that he is going to define x to the n recursive way, but supposing recursively. Or for some natural number n, then we define x to the n plus 1 is equal to x to the n times x. That's how we define. In other words, in our language, he says x to the 0 is 1. He is going to use induction. Suppose we know the meaning of x to the n for some integer n, which is different from 0, then including 0 actually, then x to the n plus 1 is x to the n times x to the x. Inductive definition. Definition 5.6.2, exponentiation a real number by an integer. Let x be a non-zero real number. Then for any negative integer minus n, we define x to the minus n is 1 over x to the n. I guess these are, just reading. Clearly these definitions are consistent with the definition of rational exponentiation given earlier. We can then assert all the properties in proposition 4.3.10, 4.3.12 remain valid if x and y are assumed to be real numbers instead of rational numbers. Instead of giving an actual proof of this proposition, we shall give a meta-proof, an argument appealing to the nature of proofs rather than the nature of real and rational numbers. Meta-proof is not actual proof but meta. If one inspects proof of proposition 4.3.10 and 4.3.12, we see that they rely on the laws of algebra and the laws of order in the rationals. But by proposition 5.3.11 and 5.4.7 and the identity xx is equal to minus 1, equals x minus x, both are equal to 1, we knew that all these laws of algebra and order continue to hold for real numbers as well as rationals. Thus we can modify the proof of propositions, these two to hold in case when x and y are real. So it's a matter of writing actually, for a bunch of writing anyway. Now we consider exponentiation to exponents which are not integers. We begin with the notion of nth root, which we can define using our notion of supremum, he says. Let x greater than or equal to 0 be a non-negative real, and let n greater than or equal to 1 be a positive integer. We define x to the 1 over n, also known as the nth root of x, by the formula x to the 1 over n is supremum of y belongs to R, y greater than or equal to 0, and y to the n less than or equal to x. That's how he is defining. The same way he defined the square root, no? Over there he took x squared less than or equal to x squared less than 2. So that's we often write square root x for x to the 1 half. Same thing here. X to the 1 over n is again a supremum of all numbers, non-negative numbers, that satisfies y to the n less than or equal to x. Same way we define square root x. No? We did not say it is square root x. Over there we said supremum of all the real numbers, non-negative real numbers, x such that x squared less than or equal to. So here, instead of x squared, here you have x to the n. No? Now we denote where am I? Now we do not define the nth root of a negative number. In fact, we will leave the nth roots of negative numbers identified for the rest of the book, undefined for the rest of the book. One can define these nth roots once one defines the complex numbers, but we shall refrain from doing so. Just nth roots, if you want to talk about the nth roots, you have to know about complex numbers. But by the way, for some numbers, you can find 1 or 2 nth roots. Because, for instance, if you take plus 4, plus or minus 2 are second roots, no? But if you take 3 x squared, third root of 3 is not that easy, but there is one, no? We call it principal third root. Do you have? No? Okay, let's forget about that for the time being. Existence of n truths. Let x greater than or 0 be a non-negative real and n greater than or equal to 1 be a positive integer. Then the set of all y belongs to R, y greater than or equal to 0, y less than or equal to x is non-empty and is denoted and also bounded above. In particular, x to the 1 over n is a real number. Now you have to sort of keep in mind that x to the 1 over 2 we define by supremum. That's how we define x to the 1 over n also. Same way, we have the set E is set of all y belongs to R such that y greater than or equal to 0 and y less than or equal to x. Over there we had y less than or equal to 2, no? X square is less than or equal to 2. Same way. So, because it is the same thing, I will not go through the proof, but if you cannot understand, you have to ask me. So we should not skip anything. If you want to learn, not A-level maths, campus type maths, no matter which book you use, if you do all the problems from the book, whether you solve it or not, if you try really hard, you learn a lot. Not only from this book. Let x y greater than or equal to 0 be non-negative reals, let n greater than or equal to 1 be positive integers. I am sure you can do it. Maybe the easiest exercise, no? That's the easiest way if you cannot do it. I make a joke also about this when I teach in the universities. I give you hard problems that I cannot solve. I solve easy problems of the world. That's what I do. The observant reader may note that this definition of x to the 1 over n might possibly be inconsistent with our previous notions of x to the n when n is equal to 1. But it is easy to check that x to the 1 over 1 is equal to x and x to the 1 y. So there is no inconsistency, he says. I mean, there are no big deals. One consequence lemma 5.66 is the following cancellation rule. If y and z are positive numbers and yn is equal to z to the n, then y equals z. Why does this follow from lemma 5.6b? We did not do it, so cannot reply, but it must be positive. Must be positive. Otherwise it's not going to work. Note that this only works when y and z are positive. Oh, it is written here. For instance, minus 3 squared is equal to 3 squared, but we can conclude from this that minus 3 is equal to 3. Now we define how to raise positive number x to the rational exponent q. So these are, construction. You should have seen them once, but you don't have to try to remember these proofs at all. You don't do that. Let x greater than 0 be a positive real number and let q be a rational number. To define x to the q, we write q is equal to a over b for some integer a and a positive integer b. And define x to the q is, we know how the meaning of x to the 1 over b, then x to the 1 over b raised to the power a. However, because a is an integer, did we define x to the negative powers? I cannot remember. Anyway, what I was going to ask is, he defined this way, x to the a over b is x to the 1 over b raised to the power a. One can define other way, it is, you take x to the power a, then take the power 1 over b. Note that every rational q, whether positive or negative, maybe it is an exercise in the book, I didn't read the exercises for this part. whether positive or negative or zero, can be written in the form a over b, where a is an integer and b is positive. Why? He is asking. However, the rational number q can be expressed in the form a over b in more than one way. For instance, 1 over 2 can also be expressed as 2 over 4 or 3 over 6. So to ensure that this definition is well defined, we need to check that different expressions a by b give the same formula for x to the k. So that is an important result. Let a dash be integers and b dash be positive integers such that a over b is equal to a dash over b dash, and let x be a positive real number. Then we have x to the 1 over b dash raised to the power a dash must be equal to x to the 1 over b raised to the power a. Otherwise, x to the rational power is not well defined. So I will not go through the here. This is not difficult, but it is an important one because one can write 3 over 6 and 1 over 2. So somebody may take x to the 1 over 6th power, then third power. Somebody can say take different quotients. So they all of them must give the same thing. It is an algebraic thing. Finally, suppose that a less than 0. Discuss here. Thus, q x to the q is well defined. For every rational q, note that this new definition is consistent with our old definition for x to the 1 over n. Why? And is also consistent with our old definition for x to the n. He is asking why. Because replies they all have all defined in the same way. Here is a lemma. Some basic facts about rational exponentiation. I thought it is an exercise that should make exercise. So we have so many exercises to do here. X to the q is supposed to be real. X to the q plus r. All the standard results. Prove it once. Don't try to remember how it was proved. It's no use. But you have to know that to show that the system is consistent. That's all. We still, to do real exponentiation, in other words, we still have to define x to the y where x greater than 0 and y is a real number. That is difficult, but we will defer that until section 6.7 once we have formalized the concept of limit. X to the y. Now, for instance, I ask you what is the meaning of 3 raised. Now, if I ask you 3 to the 5, you know 3 times 3, 5 times. If I ask you 3 to the 1 over 5, then that is a number x. If you take 5 times, multiply 5 times, then answer must be x. So you have some explanation. But if I ask you 3 raised to the power square root of 2, 3, you know how to compute that, no? 3 raised to the power square root of 2. You can compute it, no? From a calculator. But what does it mean? Kind of funny, no? 3 raised to the power square root of 2. So that's why, maths sometimes become kind of amazing. We calculate 3 to the power square root of 2. We cannot tell anybody what it means. You cannot say you multiply 3 square root of 2 times. Nothing like that. So, you don't know the definition, I guess, today, but we don't want it. The reason I emphasize that is that because certain things here, we don't know till we die the meaning of it, but we use it. 3 to the power square root of 2, if somebody asks you what is it, you have to say, I don't know. But from a calculator or computer, you can compute it. That's all. In the rest of the text, we shall now just assume the real numbers to obey all the usual laws of algebra, order and exponentiation. Like that. whole bunch of homework to do. I was thinking, because if I do it and give it to you again, you don't learn. Because you have to make your hands dirty in order to learn, no doubt. But so many exercises, doing them is very, chapter 6. Let's not start chapter 6 today. So, I don't know what to tell you, because you have to do the homework, but there is a lot more to do, no? And you got only one set of homework graded. I don't know. I was thinking because doing all the problems, certain exercises are easy. You have pointed out that
Yeah. So shall we stop the video?
you said that I agreed for two things to you for next day, no? One is that proof. What is the other thing? I cannot remember.
Do some questions with us that thing.
No, today, I did not prove this 5.5 existence of least upper bound. I agreed to do it next day. Then I agreed for something else also for next day. What is it?
Friday.
Yeah.
To do some homework questions with us which we couldn't do.
No. Today.
Today?
Yeah, today I promised to do some other thing next day. What is it?
No, that's it.
We cannot explain this next day. That is we are not going to do concavity. This, studying this also very interesting, concave functions. You can now learn this logic. Logic, quite a lot of logic.
So shall I stop the video?
No, I'm sorry? Yeah.
Yes, sir.
Yeah, enough.